Good morning. That's easy to see who my early risers are. We'll get started here in a few minutes. Still not quite yet 8 o'clock. Okay, I'm going to check and see if everybody can hear me. And I'll just put the question out there on the chat just in case. Well, that's an interesting feature of Zoom I wasn't aware of. You guys can actually chat directly with everyone without me seeing it. That's kind of the equivalent of passing notes in class. That's kind of cool. So I think I know who everybody is that's logged on, but I don't recognize who Avery T is or who, there's one of you who's actually dialed in, looks like on a cell phone. Could you guys either unmute and tell me who you are, or on the Zoom chat type in your name? Okay, got you, Avery.
This is Caitlin Frierson dialing in.
Okay, great, Caitlin, thank you.
Mm-hmm.
Perfect. All right, well, so I'd love to have more to get started, but we're going to go ahead and get started to honor the time of you folks who have gotten in on time. Today we are going to be talking about mutexes and resource sharing. And so that's a little bit like semaphores. It actually is a derivative of semaphores, but it's used for a very specialized purpose, and we'll see what's going on here. So as you remember from last week's lectures, we talked about using one of the uses of a semaphore is to lock a resource. So let's talk about this particular example that I have up here. And in this case, the resource that we're locking is a serial. And the reason that we're locking on that serial port is that we want to make sure that two different tasks aren't trying to basically intersperse the strings that they're printing out to the serial port, but will in fact do them one at a time. And we do that by having this semaphore. Whenever you call UART puts, which puts a string out to the UART, we do this semaphore pinned here that you see. And if the resource is being used by another task because somebody else has used UART puts to put their string out as well, when the second task hits this semaphore pinned, it's going to wait until somebody posts to that semaphore before it goes and does the rest of the code. If it's the first call into UART puts, then what happens is that this semaphore pinned effectively tells everybody else, wait until I'm through. He does his while loop that prints the string out to the buffer, and then he does a semaphore post, and that releases the UART. And for many cases, that works pretty well. The problem comes in something that we call priority inversion. Priority inversion is, by definition, when a lower priority task obtains a semaphore, and while that low priority task has the semaphore, a higher priority task has to wait on it. What this means is that mid-level task might prevent the lower priority task from completing its use of the semaphore as quickly as we would like to, so the high priority task is delayed. And the best way to talk about that is to look at a diagram of what priority inversion looks like. So think about what you see here as relative priority of the task, the lower priority task being low on the sheet, higher priority task being higher on the sheet. So let's say that you are task A and you're tootling along. You need to print something out to the serial port. And so you pinned on semaphore A, that serial port semaphore, saying, hey, look, I'm going to be writing stuff out to the serial port. And you're just merely writing things out to the serial port. Well, in the meantime, an event occurs that makes task B become ready. Maybe it's a timer that's timed out. Maybe it's another semaphore that he's been pending that got posted by an interrupt function. There are lots of different reasons that task B might become ready in the middle of task A operating. But let's say that he does. So when task B becomes ready, we go off and we start executing task B because it's the higher priority task. So we're going down to task A, get interrupted, we go to task B. So task B does a little bit of stuff, and all of a sudden he needs that same semaphore that task A had. Well, task A, as it turns out, still has that, but he's a relatively low priority. And oh, by the way, this mid-level priority task, task C, has become ready in the meantime. So instead of task B returning control back to task A, it returns control to task C. Task C gets ready to run. He does his thing, and now task D is ready to run, and then task E. These are all higher priorities than task A. In the meantime, task B has been paused all of this time while these other tasks that are intermediate priority get executed. Finally, task A is going to resume after we get down here and we've executed all of this stuff. Task A eventually finishes with the semaphore he posts, and then task B can resume. So as you can see, task B has been stuck all of this time, and this time in particular, waiting to finish execution, even though he's a high priority task, because other things have popped in that are higher priority than task A. So that's clearly not behavior that we want to happen. So how do we address that? Well, the way that we address that is with a thing called a mutex. So a mutex is very similar to a binary semaphore. They don't call them semaphores, and sometimes they actually are called mutexes or mutex semaphores. In this particular case, in the TI-RTOS, they call them gate mutexes. And there are multiple versions of gate mutex. So once again, TI has done something weird to enhance performance that is really not very useful in an operating system. So there are multiple types of gate mutexes supported by the TI-RTOS. The one that they talk about mostly, it does not have this PRI suffix on the name, so it's a gate mutex. The problem with the way that TI has set up gate mutexes without the PRI extension is that they, again, ignore priority, much like the default on setting up semaphores. So we're not going to go there. We're always going to use gate mutex PRI. And enter, and gate mutex PRI enter causes a calling task to own the mutex. But in essence, that is very similar to and performs the same function as a semaphore pinned. Enter and pinned are the same thing, and leave and post are the same thing. Now, again, I'm telling you they work like semaphores. TI's convention actually is kind of an interesting way to view it, because they use the word gate to describe these devices. So basically gating your access to a particular resource. And from that standpoint, this notation actually makes it a little bit easier to understand what it is that you're doing, because you have the concept of the gate, and we can all pretty much get we're going to enter into the gate to get to where the resource is, and then we're going to leave where the resource is, closing the gate behind us. So here's what's different about a mutex from a semaphore. If you pinned, which would be the enter call, on a gate mutex, and that mutex is taken, so you're going to pause. If the task that currently owns the mutex, so that's the one who did the successful enter and did not pause, if that task has a lower priority than the task that's waiting, the operating system is going to raise the priority of the lower priority task until it actually executes the leave function or does the post. So in essence, what's happening here is that we have we have the priority of this low priority task all of a sudden becomes a very high priority task. So let's take a look at what that looks like. So same scenario, except now I'm using a mutex instead of a semaphore. Task A, he pins on this mutex. Task B becomes ready. He now pins on that mutex, that same mutex that task A has pinned it on. And what happens is that the priority of task A gets changed from down here to a high priority task up here until it posts the mutex. And when that happens, task B then resumes, and then task D and C and all of that good stuff. So let's go back 2 pages. So here, task B had to wait all of this time while these 3 mid-priority tasks executed. Here, task B task A gets to finish up what it's doing as quick as it can so the task B can resume. Now, let's talk about any task that's using a mutex resource. One of the things that you want to make sure with using a mutex resource, since it will artificially elevate the priority of a task that would otherwise have a lower priority, you want to make sure that anytime you use a mutex, that you use it for the absolute minimum amount of time it takes to protect whatever it is that the resource is that you're using. So if we go back here and we look at this example function that I had, and we were going to replace these with a gate enter and a gate leave. This is relatively appropriate, but if I had some computation about what was going to go in out string, if I was going to check out string to see if it had a null terminator, if I were going to free the memory associated with out string, all of those things, because they don't have to do with what the semaphore, with what the resources that we're protecting, we would want to do those before or after we actually do our posting of the resource. Also, if you have logically distinct operations, it's a good idea to free up the resource in between those logically distinct operations. And you'll see that in an example that I'm going to go through today. Are there any questions so far? Give it a few minutes for anybody who might want to type in a question on the chat group or unmute and say something. Okay. So let's talk about the important calls that we have to deal with. So similar to what happens with other TI calls, you have this param structure initialization. What's interesting is that if you actually look at the contents of that param structure, there's nothing in there that you would ever want to manipulate. So different from semaphores and from other things, in gate mutexes in the TI operating system, you have to use the params inet. That's required because there's some underlying structures that have to be initialized. But there is nothing that you're going to want to manipulate in those. So constructing the mutex is pretty much the same as everything else that we've ever done. Getting the handle is the same. There is a little bit of there is a little difference here between this and mutexes. There's this concept of a handle. So you'll notice that this gate mutex pry enter returns an integer value. And it's a handle. It's called a handle. Basically, it's a unique identifier for the instance of this particular mutex pin. And it has to be passed to the post, the mutex leave over here when you get ready to post the mutex. The reason for this is that TI is doing some stuff in the operating system to try to avoid having a task that wasn't the one that actually owned the resource from freeing it up prematurely. So if your code is all doing what it's supposed to do, that's actually not possible. But this is kind of a belt and suspenders design. I don't have a big objection to it. There is nothing other than the fact that you have to save that handle and then return it when you get ready to save it when you do an enter and return it when you do a leave, that you have to do with that information. It's not useful information to you as the caller, but it is useful information to keep the mutexes straight at the kernel level. So I'm going to give you an example. I'm going to talk a little bit about that LCD display sitting on your Edu board, what's EduMark 2 board. So that is 128 by 128 character color LCD display. And TI has graciously provided us with a library of functions that allow us to draw pictures, write text, that sort of thing to that display. And that's really gnarly. Unfortunately, they didn't make it so that it was compatible with TI RTOS. It uses the basic GPIO library, the driver lib, as opposed to the libraries that are associated with the RTOS. And the problem there is that number one, if you don't use the RTOS library, you're going to get into trouble with having to communicate over the SPI port because all the RTOS drivers think that they're in control of the SPI port. They'll take over and do bad and ugly things to you. And of course, you don't want to have to include multiple libraries for manipulating GPIO pins, that sort of thing. So we have to modify it. And the good news is you don't have to modify it. I have. And I'm going to show you how I did that. And this is actually a pretty good lesson for anytime you're taking somebody's code and trying to think about it and make it more compatible with use in an RTOS. So, first thing that you should know about is that there is this thing called grlib. It's a directory in Code Composer Studio that is part of your project, and it contains a bunch of C files. So there is a directory called fonts, and in that directory called fonts, there are a bunch of C files that are that each have structures defined in them, and those structures, in fact, are just constants, an array basically of constants that are used to figure out which dots to turn on and which dots to turn off for particular letters of the alphabet or particular graphic symbols. So each one of those is obviously going to take up some flash space, so you don't want to put a zillion fonts on this thing. In the example that I've provided for you guys, I believe I've got 4 fonts that we've defined, but in the TI library directories, there are more fonts that you can simply copy over to that directory if you want to use a different font. The grlib directory has a whole bunch of C files that are associated with being able to do different things. So if I wanted to write a string, a text message, if you will, to the display, I can use this function called graphics drawString, or if I want it to be centered, I can in the display I can use graphics drawString centered, and it will take a look at the characters that I'm trying to display. It'll get the fonts, it'll do its thing, and draw that on the screen. And so there's a whole bunch of those. So there's a button.c that draws buttons on the screen. There's a box.c. There's a circle.c. There's an arc.c, line.c. All these things that have these graphics functions. And TI has done a good job of documenting those in the file, so you can go and take a look and see what it is that you want to use to draw various elements on the screen. Then there's this other directory called LCD driver directory, and it's divided into 4 files. There is a Crystal Fonts 128X 128 ST7735. Magically, The manufacturer of the LCD display is Crystal Fonts, and their part number is ST7735, and it happens to be 128 by 128 pixels. Amazing. How did they come up with that file name? We will never know. So in that file, there are 3 functions that are available for global use. There's this init function, there's a frame, set draw frame function, and a set orientation function. So the 128 by 128 init, that particular function is basically calling whatever it takes to initialize the display controller in whatever way that it needs to get initialized. Set orientation tells you whether you want the display pointed up, pointed down, pointed left, pointed right. So you can actually draw your text on it as rotated, if you will. So we could, with this, if we detected that through the accelerometer that's on that edgy board, if we detected that you were holding the edgy board upside down, we could actually flip the display so that it would be readable. And this set draw frame is the final piece of initialization that actually sets all the pixels to whatever value that you need them to be. The good news is none of that stuff needs to be altered, because that all seems to be, from my reading on the code, 100% compatible with, it's all reentrant code, it's well written, and it doesn't access the hardware in any way that uses the important operating system calls. However, this thing called HAL MSP, EXP430, 401R, Crystal Fonts, etc. This is all of the low-level, very specific code that it takes to for the Crystal Fonts LCD driver to write something out to the display. And so there's write command, write data, port init, and SPI init are the functions that, that they have defined in here. So if we look in this particular file in the .c file for this, first thing that you're going to find is this HAL LCD SPI init. Now, what we're going to do to make this thing compatible with what, actually, I've got these reversed, because this is the one that came out of their original stuff, because it's using the SPI master enable. So actually, this arrow is going back the other way. This is, in fact, let's fix that. There it is. You got 2 files in the same directory that have the same name, but slightly different code. It is sometimes confusing. So this is where we're writing to the I/O pins. This is basically setting up the chip select and register select pins for the LCD display. And here we're getting all the ports initialized. This was the original code, and we're over here setting up the SPI port because the bits were set up in the other function call. And then let's take a look at the command. So you can take a look at what the original command was. So like this HAL write command. Basically, what it's doing is that it's pulling, this is a register select pin on the LCD display. If you've used SPI before, you know that sometimes there's this register select pin that tells you whether I'm actually writing data to it or I'm writing to the command register. So write a command, we pull this pin low, and they get into a while loop to wait to make sure that the SPI isn't busy, that anything that's happened on the SPI is done. Then it puts the command that you want to transmit into the SPI buffer, and then it waits until the SPI is not busy anymore, and it sets that pin back high. So we have to do the same thing with the OS. And in this case, what we're doing is that we're writing out to the IO pin, just like they did, to set the register select. And then we're using the SPI transfer that is part of the kernel. And so we're setting up the number of bytes to transmit. We're setting up the actual byte. We're pointing to the actual byte that it's going to transmit, which is this command byte. And the SPI transfer stuff actually always reads off the SPI every time it writes to the SPI. So you have to have some place for that data to go, and that's this dummy variable here. Imagine why I named it dummy. We're going to do a transfer. So this actually causes the transfer to take place. Now what's really cool, since this is OS aware, if you had something else going on while this is happening, the processor does not stop doing other things. So you could have other tasks that would be resuming while you're in the process of this transfer. And then once the transfer is complete, we go ahead and we set the register select pin back to a 1. Similarly, if we're going to write data, the only difference, if you take a look at this code, the only difference between write command and write data in the original code is whether or not we set this register select pin, and so it looks exactly the same. So now we've got another issue that we have to think about. All of the SPI functions require that the OS is running. You say, well, why is that a problem? Well, the problem is that you've got to, if you've got multiple tasks that are going to be potentially talking to this LCD controller, you have to initialize the LCD controller. But you can't initialize the LCD controller unless the operating system is running. Well, once you get the operating system running, the only thing that is running are tasks, but I can't guarantee the order of execution of a task. If I have 3 tasks that I initialize, which one actually starts first is based on priority and on issues where you have the same priority, a certain amount of, it's not really random, but it's unpredictable. It's not something that I can plan on in my design process. So what do? Well, what we're going to do, and this is a technique we're also going to talk about with reference to keeping track of the health of your program much later on in the in this class. What you have to do is that you actually have to start a single task whose function it is to perform initialization and then start the other tasks. So you don't have to have all of your tasks running when you start a program, but what you do have to do is that you do have to have this initialization. So if I only have one task running, I know that it's executing before the other task. So here's how we're going to do that. By the way, this is code that I'm providing for you to help you do your next homework assignment, and it's all in a portable Code Composer Studio export. The same way that you turn in your homework to me, I am providing this template for you guys. So one of the functions that I'm providing for you is this main function, and so you're going to recognize pretty easily the board initialization, initializing the GPIO, initializing the SPI. You got all that. You know how that works. It's no big deal. And then I call this thing called task start display task. And we're going to look at that in a minute. But one of the conventions that I use, because I am one of the things that I believe in very strongly, is that I believe that it is good to hide data that other tasks don't need to know from those other tasks. So I put each individual task into its own C file, and I provide what I provide to interface to that task is a function called start something task. That's the convention that I use for naming. And its job in life is to do whatever initialization it takes to start the task and then register the task with the operating system, as we're going to see. Turning off the LED, that's no big deal one way or the other. It's just something that I chose to do to make things a little bit easier, and also let me see status, and you'll see how that works in a moment. And then we start the operating system. So let's see what this start display task looks like. So in start display task, we have some local variables. We have the task params, and we have the mutex params, because we're going to create the mutex in the task. So I have declared, not showing it here, but you guys, when you look at the code, can see, I have declared my gate mutex structure that's associated with my mutex statically in this function. Mutex params comes from there, and so we initialize the params, we construct the mutex, and then this display gate is the handle for my gate mutex. This is global. Anybody who wants to talk to the display can grab a hold of display gate to be able to exercise the mutex that's going to be associated with using the LCD display. Then I have to create my my display task, and I have this display stack size. Now I have set up the display stack size to be larger than the default 512 bytes. And the reason for that is that there are a lot of local variables and stuff that get used anytime that you're talking to the display. So you're going to need a little bit larger stack size for any function, for any task that you're going to be using the display with. So tasks that don't use the display can be down in the 500 byte region for a stack size. Tasks that do use the display need to be a little bit larger, and whatever I define that as externally is a pretty good starting place for that. So we provide the address for the display task, we set the priority for the display task, and then we construct it. So this function right here, this function right here, as we talked about before, that tells the operating system, hey, here's my task. Whenever you get around to it, and the actual task name is display task, the actual function. When you get ready to activate this task, it's that function right there, and this is the structure associated with it. So let's look at display task. So I have some local variables that I'm here. This title box I'm going to be using here in a little while. It basically is something that's used when we get ready to set up just a colored box on the LCD display. We'll talk about that in a minute. And then its lock handle I'm using with the display with the mutexes, when we use those mutexes. So the first thing that I do is that I initialize the display, I set the orientation, and then I have to initialize the context. this context is basically how all the graphics software keeps track of what's on the display. It can't really read the display, so when you alter the display, you have to know what's already there. And this graphics context is how that keeps track of it. Not important that you understand much about that, other than the fact that you have to have this graphics context whenever you're displaying something on the LCD display. So the next thing that I'm going to do is I'm going to draw a box on the screen. And I'm going to start using my mutex immediately after I get everything initialized to do the access. So here you can see I'm identifying what's in the box. Notice that all of this stuff right here is outside of my gate enter and gate leave. Now when I get ready to write to the graphics display though, and I'm doing this all at once because I don't want anybody to be able to interfere with what I'm doing, maybe change the color on me or that sort of thing, while I'm actually drawing this box. So I lock the display, and now I'm going to set the background color to white. Foreground color, they didn't have maroon, but they have dark red, and it looks pretty maroon to me. I'm going to clear the display, and then I'm going to draw this rectangle. Now, the way that on the graphics display, this is going to be basically a bar across the top of the display. And then, hey, I'm done with that. So I've done this atomic operation. And now if somebody else wanted to write to the display, it would be perfectly okay with me. And so I do a leave with the gate mutex. Going down a little bit more, we're going to write some stuff on there. So again, I'm getting ready to write the title on here. And this, by the way, take a look. There's 101 actually is just a blank line. No need to include that in any of this stuff. But this is the next thing. And you notice that I did the lock and the leave here. By the way, notice lock handle, lock handle. I did the locks and the leaves. And I'm locking these things one at a time as I'm putting this all together. So here's what I'm doing. I'm locking the display. I'm changing the foreground color to white. So I'm going to do white letters on top of the maroon background. And now I'm going to write a string, a centered string. These are the parameters that it takes to write the centered string, HW03. So that's going to be on the display. It's going to say HW03 on one line, and on another line, see this is title row 1, title row 2, which I have to find elsewhere. Those are pixel numbers. Middle pixel is also a pixel number. And then I'm going to write graphic display on the next line. Then I'm going to put the colors back to what I would consider normal colors, which would be writing in black. I'm going to set to a different font. So the font that I chose here, this set font, I have this title font and then I have a data font. This title font is bigger characters, so it looks kind of gnarly on the display. And then once I'm through writing all that stuff and getting everything set back to where it needs to be for somebody else to use the display without setting font colors and stuff, I do my leave. Now right in here, this is the part where you need to be inserting your code. So this is where, so now that we've got the display like we want it, if you want to start another task, instead of putting the start task in main, okay, where we have the start display task and all that stuff before you do a BIOS start. Your BIOS is running now, but we're going to put in whatever it takes to start our task in this section between these two comments. So before this particular display task goes into its while forever loop, we're going to put something right in here. Now, what I've done is that I have this particular task. Basically, he is blinking the LED 0 on the board. So it's kind of fun from the standpoint of when you are debugging this code. When the LED starts blinking, that says, hey, we've done everything that it takes to initialize the display task. And so again, it gives you a indication that we're successful here, other than writing the information on the display, because there may be other things happening here that take a while. So we've got that. One thing that I will tell you is that there's no reason when you do your homework that this has to be all that's in this display task. If you've got, if you've got something else that's part of your assignment that needs to happen on a regular basis, or logically makes sense to occur in this display task, in the while loop for this display task, you can put anything here. It does not have to be necessarily even associated with the display, although logically it would make sense to make it something display oriented, just so that you don't have to go hunting for things in weird and wonderful places. So that's what I've got for today. I have posted the homework 3 assignment, where we're going to be working with the graphics display. I encourage you, just as a matter of a learning exercise, I encourage you to well, fiddlesticks, I was going to do something over here. Let me do that real quick. I encourage you to take a look at the code that has been put together there. And by the way, based on grading your homework assignments, 2 things. Number 1, take a look at the sample code that I've provided you. Anything that says that it was created by Professor Willie, you should be using as an example of what I expect you to make your code look like. And read the coding standards. I get the feeling that either you haven't read the coding standards or that you've chosen to ignore them for convenience sake. I will tell you that most of the stuff that I've been taking off points for in coding standards, quite frankly, 2 to 3 minutes worth of work before you turn in your homework, and that's 5 extra points on your homework assignment. So I hope that you guys will take a look at that and start giving me code that I can be even more proud of. I will say the second assignment, you guys definitely did a better job than as a class than you did on the first assignment. I'm glad to see the improvements. So, are there any questions before we close this one out? Notice only a few of you have started on the test. It's not that hard. Review the other lectures and get the test done. That's coming up due, I think, the end of this week. All right, well, there being no other questions, I declare class dismissed. Thank you very much for your attention, and we will see you guys Wednesday at 9:15.